So our next speaker is Akshay. He's going to tell us about MPC in a very limited setting where a minimal communication is available, basically.
Yeah. Thanks a lot for the introduction. I'm going to talk about a joint work with Varun Narayanan and Shubham Vivek Pawar. The title of my talk is Secure Computation with Parallel Calls to Two Array Functions. Okay, so let me start by quickly recalling the notion of secure computation. So in this setting, we have several parties, and each party has its own private input. And the parties also have a description of some function f as common input, and they wish to compute the output of this function on their private inputs. So secure computation is a distributed computation protocol that allows the parties to learn the output of this function at the end. This is the complete or the correctness requirement. The second property we require this protocol to satisfy is the security property, which states that even if an arbitrary subset of the parties get corrupted, these corrupted parties cannot learn anything about the honest party's inputs except the output of the function. Randomized encodings is one of the key tools used in the construction of secure computation protocols. At a very high level, a randomized encoding allows us to reduce the task of securely computing an arbitrary function f to the task of securely computing a related function g. Okay, so in this methodology, each one of these parties pre-process their inputs into x1 prime up to xn prime. Then they securely compute g on their pre-processed inputs, run the output of g through a decoder to learn the output of f on their original inputs. Okay, so this is the idea of using randomized encodings. And in order for this reduction to make sense, we want g to be somewhat simpler than f. And prior works considered simplicity with functions having constant degree. Okay, so this approach of considering constant degree functions has been instrumental in constructing constant round secure computation protocols, and this actually culminated in a work by Ben Hamuda and Lin and Garg and myself, who showed that G can in fact be a degree 2 function. Okay, and this reduction was abstracted in a nice work by Benny, Zwika, and Rotem as multi-party randomized encodings. Okay, so in this work, we are interested in restricting the class of simple functions even further, and we require this function g to have constant input as well as constant output locality. Okay, so this trivially computes only constant degree functions, but we don't know whether constant degree functions can be represented with constant input and output locality. So this is the question that we are interested in. Specifically, can we reduce the task of securely computing an arbitrary function to the task of securely computing a function with constant input and constant output locality? So towards resolving this question, we consider a very simple model of secure computation, which we call as parallel calls to two array functions. Okay? So in this model, there is an encode algorithm that takes in the private input of the party and maps it into n shares, xi1 up to xin. Then each pi and pj make a call to a function gij, where pi provides the jth share, xij, as the input, and pj provides xji, that is its ith share, as input. Okay? So this function just takes inputs from two of the parties, and let's denote the output of this function as yij. And then there is a decoder which takes in all the yij's and outputs the function computed on the original inputs of the parties. Okay? So two important points to note is that the calls to all the gij's happen in parallel, so there's no delay, and each one of these gij's take input only from two of the parties. So that's why it's called parallel calls to two array functions. Okay? So it's not too hard to see that one-array functions are very restricted. You cannot compute even a non-trivial class of functions. So 2-array is the minimal arity required to compute interesting classes of functions. Another reason, and apart from being a very naturally motivated model, is that we can show that any protocol in this model can be converted into one that makes function calls to one which just has constant input as well as output locality. So thereby answering the question that we wanted to answer in the first place. And another thing is that in the semi-honest setting, we can compute any degree 2 function with parallel calls to 2-array functions. Basically, you compute each monomial, add a random masking factor, then combine all the monomial outputs masked with the random factor to get the output of any degree 2 polynomial. So in the semi-honest setting, since degree 2 functions are already complete, we can show that 2-array functions are complete in the semi-honest setting. So the question that we are interested in this talk is that, is it complete against malicious adversaries? Okay? So we have a mixture of both positive as well as negative results. So firstly, the negative result shows that unlike the semi-honest setting, you cannot compute every degree 2 polynomial with parallel calls to 2-array functions. So specifically, there exists a degree 2 function that cannot be securely computed against malicious adversaries with parallel calls to 2-array functions. And the security notion that we consider here is statistical security with abort, selective abort. We show that this negative result can be overcome if, still in the statistical setting, if we rely on a weaker notion of security called privacy with knowledge of outputs. So at a very high level, privacy of knowledge of outputs guarantees that the adversary cannot learn any information about the inputs of the honest parties, but it can force the honest parties to output an arbitrary value. Okay, so this is the kind of attack that an adversary can mount, and we show that this security notion can be achieved with statistical security. And second, we show that this impossibility result can be overcome in the computational setting. So specifically, if you assume oblivious transfer, then every function can be securely computed against malicious adversaries by making parallel calls to 2-array functions. Okay, so yeah, so this is our main result. So in the rest of the talk, let me give a brief overview of the negative result, followed by some high-level ideas on how to construct this positive result. Okay, so let me first describe the function for which we prove that there exists no secure protocol that makes parallel calls to 2-array functions. So the functionality is a 3-party function. The private inputs of these 3 parties are elements from Z4. So x1, x2, and x3 are elements from Z4. And the functionality simply checks if x1 plus x2 plus x3 is 0 or not. Okay? And this function can be written as a degree 2 polynomial over the binary. Okay? So assume, for the sake of contradiction, that there is a secure protocol that computes this function with parallel calls to 2-array functions, namely G12, G23, and G13. Okay? So now, consider an adversary that corrupts both P1 as well as P2. Okay? This adversary behaves honestly when it is interacting with the oracles G13 and G23. So the key observation that is crucial for a result is that for any Z in the range of G12, the output of the decoder on the honestly computed G13, G23, and Z is f of x1, x2, x3 or bot. If not, we can use this adversary to distinguish between the real worlds and the ideal world. Okay? So similarly, consider another adversary that corrupts P1 and P3. Via symmetric argument, we can show that for any z in the range of G13, the output of the decoder is either f of x1, x2, x3 or bot. Okay, again, if this is not the case, we can use this adversary to distinguish between the real and the ideal worlds. So now, to complete the attack, consider an adversary that just corrupts P1. So this adversary sends an honest encoding of x1 when it is interacting with G12, but it sends an encoding of x1 plus 1 when it's interacting with G13. So basically, it is using inconsistent inputs in its two oracle calls. So now, this adversary, to learn some non-trivial information, observe that all that it needs to do is to find a z in the range of G12 such that the output is not bot. Okay, so from the previous observation, since this is behaving honestly with the call to G13 using the input x1 plus 1, this output is guaranteed to be f of x1 plus 1, x2, x3, because we conditioned on that being not bot. And this adversary also finds a z in the range of G12 such that the output of the decoder is not bot, and this is again guaranteed to be f of x1, x2, x3. So this adversary can learn the output of the function on fixed x2, x3, but on two different inputs of its choice. Basically, this contradicts the security of the protocol. Okay? So this is the high-level idea behind the negative result. Let me quickly go over the positive result. So recall that the key intuition was that the adversary was able to somehow send inconsistent inputs to two different oracle calls, and in order to get a positive result, we must somehow prevent an adversary from doing this. So to prevent this, we construct a special purpose CDS protocol where we ensure that the output of this oracle called G23 gets erased if P1 is behaving dishonestly. That is, it is using inconsistent inputs in the calls to G12 and G13. Of course, the key challenge here is that all the calls are made in parallel. So how does one oracle detect an inconsistency? So unfortunately, I won't have time to go into the details, and I'll encourage you to look into the paper for the CDS protocol. So some of the other results that we have in the paper is that assuming one-way functions, we show that every function can be securely computed against malicious adversaries with parallel calls to 3-array functions rather than 2-array. And we also show that assuming just one-way functions, in the honest majority setting, we can construct a similar protocol against malicious adversaries. Okay, so one of the open problems is to construct a protocol in the dishonest majority setting, assuming just one-way functions with parallel calls to 2-array functions. Okay, so that's it. Thank you for your attention.
Questions? So I have one question. So about the positive result in a statistical setting, can you get a perfect, a positive result in a perfect security?
Yeah, this I'm not too sure whether it's possible or not. I think that our result is just statistical. Yeah.
It's the CDS, right?
Yeah, the CDS has some error, so negligible error, but it's a great problem to find if it's perfect. Perfect security is possible. PWK.
More questions? So let's thank the speaker again.